Good afternoon. I'm Miss Mikesell, and this podcast is on the molar mass of air practice lab from your lab workbook. This video is going to provide some support in the calculations, and you can watch it if you're struggling to do the molar mass of butane gas lab because the calculation process is similar, so it should give you some ideas as to how to approach and have success on that graded lab. So our essential question for practice lab 4, the molar mass of air, was to experimentally determine the molar mass of air in grams per mole for a given volume of a sample of gas. Using our percent air, we were to determine whether or not our answer was valid within plus or minus 10% of the known value. And if the answer was not valid, describe where the error took place in the procedure and how that error affected our calculated molar mass of air. Your tools for this lab were pretty simple. We were given a syringe that had a hole drilled through the plunger and a nail so that it could be locked into place, a thermometer, and an analytical balance. And I have a sample set of data that was collected. So our process is actually a 3-step calculation process. We're going to start by using ideal gas law, PIVNERT, PV equals nRT, to solve for the moles of air that was in our syringe. Then we're going to use our data from the analytical balance to determine the mass of air that was in our syringe. And finally, we'll put those two measurements together to get the molar mass of air. Molar mass is grams per mole. So if we divide the grams of air by the moles of air, we'll get molar mass in grams per mole. So let's take a look at our data set and walk through and do these calculations systematically. Step 1, step 2, and then finish with step 3. So step 1 asks us to use our data and ideal gas law, PIVNERT, to solve for moles of air. Let's start by identifying our givens. We know that our temperature was 24.6 degrees Celsius. We know that our volume was 48.1 milliliters. And our pressure was 0.810 atmospheres. We always know R as it's the universal gas constant. That's 0.0821 latim mol K, which means we're going to be solving for N. N is the moles of air. Before we can use ideal gas law, it is very important that our units and our givens match R's values so that units cancel correctly. So we can see that atmospheres matches atmospheres, but milliliters does not match liters. So we definitely need to go back and convert milliliters to liters. And we also need to get out of Celsius and to Kelvin to get those units to match up. Let's start by converting milliliters to liters. There's 1,000 milliliters in 1 liter. So if we divide by 1,000, milliliters will cancel out and we will have our measurement in liters. And then to get from Celsius to Kelvin, we simply need to add 273. Now that we have our givens in the correct units to substitute and solve, we need to identify our rearranged equation. So we're solving for N, the number of moles. To get N all by itself, we're going to need to divide both sides of the equation by R and T. When we do that, it will cancel out. So our final rearranged equation should be N is equal to pressure times volume divided by R times T. All right, we're ready to substitute and solve. Let's substitute our pressure and volume values into the top and our R, universal gas constant, and temperature into the bottom. Now note, we have a fraction within a fraction. So to clear that fraction with our units for R, the universal gas constant, we need to multiply by the reciprocal. So the reciprocal of latim mol K would be mol K over latim. And if we put that into our equation, we can now see atmospheres cancels, Kelvin cancels, and liters cancels. So once we do the math and multiply by the top values, dividing by both values in the denominator, we should have our answer in moles. It should make sense that our answer in moles is a very, very tiny number, 0.00159,461 moles of air, because our syringe was very small. At standard temperature and pressure, 1 mole of gas is 22.4 liters. Envision a 2-liter soda bottle. If you have 12 of those, you have about a mole of air. Obviously, we had way less than a mole of air in the syringe we used in this lab. So it should be logical that our answer for moles is a very small number. All right, we've completed step 1. We used our data from our experimental data set and ideal gas law to solve for the moles of air. Let's move on to step 2. For step 2, we need to use our data to solve for the mass of the air. We have 2 measurements for mass. We have the mass of the syringe filled with air, as well as the mass of the syringe empty as a vacuum. To find how much the mass of just the air was, we're going to have to subtract out the mass of the syringe. So we're going to take the mass of the syringe with air and subtract the mass of the empty syringe that we measured as a vacuum. That will give us the mass of just the air in grams. So we'll take 41.7779 grams and subtract 41.7329 grams, and we can see that the mass of our air was 0.0450 grams. All right, we just finished step 2 because we used our 2 measurements of mass and the difference between them to determine the mass of the gas in the syringe. In this case, that was air. We generally can't measure the mass of a gas directly, so we're going to often get the measurement for mass indirectly by measuring a before and an after mass. Step 3 is to solve for the molar mass of air. That means we need to get to grams per mole. Molar mass is grams per mole. So we're going to take our mass of air in grams and divide it by the number of moles of air that we calculated using ideal gas law. Note, we will now have our answer in grams per mole. Super important that you pay attention to units so you know when you get to your final answer and the value you're trying to calculate. All right, substitute this into your calculator. And then let's look back at sig figs, and we can see that our final answer should have 3 sig figs, because when we multiply and divide, we use the least precise number of sig figs. We should have gotten 28.2 grams per mole. Our final step is to calculate our percent air. And to do that, we need to know the theoretical molar mass of air. That was given to you on the lab sheet because air is a mixture, and it's got a relative fractional abundance, about 78% nitrogen, 21% oxygen, 1% argon, and then a couple of other trace elements. So to find our percent air, we're going to take our experimental minus the theoretical, the true value, divided by the theoretical, the true value, multiplied by 100. The percent sign is our unit, and it is the unit we'll put on our answer. So it's super important that the first thing we do is the subtraction step that's in parentheses. That should be done first. So we get a difference of 0.7751, and that's negative because our answer was just under the true answer. We're going to then divide that by the theoretical molar mass of air of 28.9751, and then multiply by 100. And hopefully you got a negative 2.7% air. All right, we should be able to wrap this lab up by writing a claim. Our claim is going to need to tell the reader what our experimental molar mass of air was and whether or not we are valid, and use our percent air as our evidence. So I found the experimental molar mass of air to be 28.2 grams per mole, which was valid as it was negative 2.7% from the true value. Isn't it amazing? With just a syringe, a nail, and an analytical balance, we were able to determine the molar mass of air with that much precision. Science really is pretty cool, isn't it? Have a great night.